Jun Yao is a professor at the University of Massachusetts Amherst. Yet another multi-awarded researcher. Delighted to have them all here. So, extracting electricity from the air. This, I would think, has a nice tie-in with our very first presentation from Kevin. And chatting briefly with Kevin last night, I know he's interested in this work. So, Jun, please tell us all about it.
Thank you. Thank you, everybody, for attending the conference, and thank you to the organizations for the invite. This is my first time attending the TTI Vanguard conference, and it's also a learning opportunity for me. I've learned the AI, brain-machine interface, and power electronics. So I'm going to talk about something kind of more basic to all those, that's electricity. More specifically, the feasibility to harvest electricity from the vast air. I chatted about this topic with some fellows, I think the other day, and they thought this is kind of sci-fi story. So I will leave you to gauge if this is sci-fi after this talk or it is not. Hopefully I can finish the talk. So I'm going to move this. So this is a chart for the US electricity production, and you will see that at the bottom, these are the so-called clean electricity. And you see that the nuclear and hydropower, they still consist of a big portion of the clean electricity. But you see that their trend is pretty much flattened. So what's picking up are the solar and the wind technologies. I think this is easily appreciated, because compared to, for example, hydro power, solar and wind, they are natural resources. They are less confined to geographic conditions and easy accessible for expansion. There is even more accessible natural resources. That's the atmospheric humidity or air water. I think we don't necessarily realize that there's electricity contained in it, unless we are reminded by, for example, the lightning during the thunderstorm. And in fact, the air water can be considered as a second form of solar energy, because eventually about 50% of the solar absorption goes into evaporation. And certainly part of that energy goes into the electric or electrostatic form. And that's why we can get the electricity in the lightning during the thunderstorm. A lightning flash can contain a lot of electricity. There's actually an interesting estimate. If we can collect the electricity across all the lightnings across the world, it can come closer to powering the entire US household for electricity usage. But of course, the historical attempts to capture electricity from lightning are all failed, and now are deemed hopeless. Now, we had this kind of a serendipitous discovery of a device we call the air generator, or AirGen for short, that can show the feasibility of capturing electricity from the air or the air water in a continuous and a controllable way. I think this may give some alternative hope for this long-term dream of capturing electricity from the vast air. So I will introduce the AirGen by going through how we initially fabricated a prototype. The initial AirGen was fabricated from certain type of biomaterial. It's synthesized by bacteria. It's got a geobacter that lives in the river mud, which was discovered by my colleague, microbiologist at the UMass Amherst, Derek Lovely, about 3 decades ago. So you see that they synthesize these kind of long filaments. Now, each filament is very small in size. It's about 10,000 times smaller than the human hair. So we use this term nano to describe their small size. And of course, they are made from biomaterials, of course, precisely protein. So they are also called protein nanowires. So the bacteria, they use these protein nanowires as if they are small cables. They can do charge or information exchange with the environment or its own species, which means that these nanowires are constantly exposed to the wild environment, which means that they have to be designed with environmental stability. So Derek and his team, they have developed ways so they can culture many of those cells or bacteria in the lab environment with a renewable feedstock, and they can share off those protein nanowires, purify them, and suspend them in the water solution. Now you can imagine if you drop a water solution on the surface, you let it dry, these protein nanowires, they're going to precipitate to form or pack together to form a thin film. It's also called a protein nanowire thin film. The prototype reagent was made from this type of protein nanowire thin film, which still has a thickness only about 1/5 the diameter of a human hair. And it's sandwiched between a pair of gold electrodes. Now we use gold because gold is inert, which means that it does not react. So any signal we pick up is not the artifacts contributed from other materials, contributing from the protein nanowire itself. So the top electrode, you will see that in the schematic is small. It's small, so that the entire top interface of the thin film is exposed to the open air, whereas the bottom interface is sealed. So the bottom image shows a prototype image device. You see that this yellowish half-transparent region is the protein nanowire thin film sandwiched between a pair of gold electrode. The top gold electrode is really a thin golden wire, right? And the bottom interface is a thin golden film deposited on glass substrate. So nothing too fancy. I suppose everyone here, if I give you the materials, you can do that. Now, if we use a voltmeter to measure the voltage across the two electrodes, you will have a reading about 500 millivolt, or about 0.5 volt, from the device. And we know that the AAA battery is going to give you 1.5 volt. So this 0.5 volt is a decent value, particularly it's coming from a thickness is only about 1/5 the diameter of a human hair. And this voltage sustains. So the black curve shows that continuous 2 months recording. You see that never decays. In fact, 3 years later, we plug in the voltmeter for measurement, it's still there. So it's sustained, and it's actually independent. One is that it's day and night in the dark night, which means it's not coming from the light as the energy source. Second is that it's independent of the oxygen content in the air. And again, we mentioned before that the electrode itself is inert, which means that it does not react with any kind of substance. So putting together, if you have some chemistry background, that means the energy is still not coming from any kind of pre-stored chemical energy in the device, right? It's not coming from the material decomposition in it. So in the end, you will see that the output is correlated to the air-water concentration. That's the relative humidity, the blue curve. And I will talk a little bit more details later about why the air-water is the energy source. Now, precisely speaking, if a device gives you a constant sustained voltage output, that doesn't mean that it's a generator, because a battery can give you a sustained voltage, but it's not a generator. It's just a storage device, right? It stores energy. It does not produce energy. How can we see or tell that the reagent actually is generated? The simple idea is that we use that device to power up another device, and we can monitor its energy level. If the energy level is somehow replenished, we know that the energy is being generated in the device. So here is a simple test. We just connected the prototype device with an external device, in this case, a resistor. Now you will see that the reagent can supply continuous electricity. That's the red curve. It's about 20 hours. And then you measure the voltage in the reagent device. That's the black curve, right? You will see that the voltage reduces to a certain level. That means the energy is being used up in the device. But let's say if we stop the usage, you will see that block curve climbs up to its initial value in the air. So that means the energy is being replenished in the device. Now this process can repeat, right? So in that way, you see that the AirGen device behaves like a rechargeable or self-recharging battery in the air, or in other words, that the electricity is being generated in this AirGen device. Now, you can certainly use other storage device, for example, a capacitor, to capture the electricity from the AirGen device and power up, for example, LED display. I show this because some people only believe in seeing something lighting up than a curve to believe that the electricity is being generated. Now, how AirGen can capture electricity in the air water? So this is a so-called high-resolution electron microscope image of the protein nanowire thin film we used to construct the prototype. You pretty much can see that it contains many of those filaments. Now, keep in mind, each filament is a single protein nanowire, and it's 10,000 times smaller than the human hair. So you can also get an impression that there exists lots of small holes in this film, right? And in fact, the protein nanowire, it has the helical structure. The top image is a computer model. So its surface is not completely smooth. So it has these kind of periodical bulges. So you can imagine that even in the most compact packing configuration, in this case, let's say 2 nanowires, they bundle together, right? There still exist these kind of nano scale holes. All right? Again, we use a nano term to describe the small size. There still exist these kind of holes at the wire-wire interface. So that means there contains lots of those kind of nanopores in this AirGen device. Now imagine we're gonna cut through the AirGen device vertically, right? And what you see is imaginary, the cross-section of the AirGen device. And you will see that there are multiple protein nanowires. They pile up to form the thin film. And you also know that within each layer there contains lots of these kind of small holes, nanopores. Now you can also imagine that these nanopores, they will align in the vertical direction to form a small channel. Again, we call it a nano channel. So that the water molecule in the top, in the open air, they can go through this channel from the top, open the interface, down to the bottom, seal the interface. Now, we mentioned before that the nanopore size is very small, which actually is not too much bigger than the size of a water molecule. So that means these kind of water molecules, they're flying, through the pore, they can easily bump into the surface. That is the protein nanowire surface. So that means, before they can travel along the channel. So that means the top layer of nanowires, they will be bumped more often than the bottom sealed nanowires, right? From these kind of water molecule coming from the top. I think this is easy to appreciate because it's like in a forest. The top layer of trees is going to receive more sunlight than the bottom buried layer of trees, right? Because sunlight comes from the top. Now I'm going to show you a phenomenon that I think every one of us can appreciate. During a dry and cold weather, when we touch on the doorknob, we sometimes got the electrical shock, right? So the electrical shock comes from the fact that our hand and the doorknob, they have different level of charges, right? So when the two come closer to each other, the charge will redistribute to form a new balance. This kind of redistribution process involves an instant charge transfer. That is the electrical shock. Now this is actually such a common phenomenon. Essentially, any two dissimilar objects, they come closer to each other, there will be instant charge transfer. The electrical shock is just such a big one that we can feel, right? So if we take this kind of instant charge transfer into the consideration, we will begin to understand how the agent works, right? So imagine that every flying water molecule, they bump into the nanowire surface. It's just like our hand is touching on the doorknob. So there will involve instant charge transfer process. The water molecule in the air, it's a very efficient charge carrier. And that's how or why we get they can supply the charge, or for forming the lightning during the thunderstorm. So that means a fresh water molecule comes in, bumping into the nanowire surface, is going to donate small portion of charge to the nanowire surface. We mentioned before that the top layer of nanowires, they're bumped more often than the bottom layer of nanowires. So that means over time, the top layer of nanowires, they're going to receive more charge than the bottom layer of nanowires. So that means that over time, there will be charge separation or imbalance being built up between the top and bottom interface of this agent device. So then, if we connect the top and bottom interface, you will see that the charge will flow to cancel out or smooth out this kind of charge imbalance in the device. So this kind of flow of charge, that's the electricity being generated. Now, this is not the one-time thing, because the open air provides huge amount of fresh water molecules. They come and go to donate new charges. So this process, the energy harvesting process, can continue. I'm just going to give you some quick tests to show why the air water is the energy source as we analyzed. We know that in a solar panel, you have a question?
Yeah, I'm just a little confused following this. Like the explanation that you gave made sense, but it feels like that same explanation would say that like every surface should have a half a volt of charge if it's got one side exposed to water vapor and the other side isn't, right? So like, why does this material collect that charge and produce that half a volt, whereas like my arm doesn't, or something like that?
That's a really, a hidden point question. I will show you that this indeed is a generic effect, right? I just use a protein nano as an example. We'll get to that. Thank you. So I'm going to show you some quick tests to show that the water molecule actually is the energy source. We know that in a solar panel, if we block the sunlight, the energy is gone, because sunlight is the energy source. So in a similar way, if we block the water, air water, by sealing the top interface of the agent device, you will see that the electricity generation is stopped. Anytime we remove the seal, you will see that the energy generation is resumed, right? Now, in a solar cell, we also know that in a bright day, you will get more electricity. So here, the same case. If we increase the air water concentration, or that's the relative humidity, you will see that the energy production is also increased in the agent device. So these kind of simple tests is going to show us that really air water, or more precisely, the air water exchange is the energy source of the agent devices. So as if the device is filtering the charge from the flying or passing by air water for electricity. So what does that mean? This means that this is a completely clean process. The air water molecule is still air water molecule. It's only the charge that's being taken. No other substance is created or consumed. So it's a completely clean process. Second, this is a sustainable mechanism, because, as I said, the open air has huge amount of fresh water, air water molecules. They're going to come and go and continuously supply the energy or the charge.
Question, can you go back one slide? So I'm a little stuck too, because you're only talking about 100 nanoamps
Correct.
current is
Correct.
produced, and even many microprocessors still require microamps to even in sleep,
yes.
deep sleep mode. So how much would you have to scale this up to be practical?
We'll come to that.
Okay.
Later, yeah.
Well, you should do that sooner, because because right now it doesn't look practical at all, and I can see why you're getting challenged on this.
That's a good question. I try to entice everybody so before we can. Yeah, it's a strategy. So anyway, that's getting on to the first question. So you see that to this moment, we used the agent made from this, so you can say it's a type of bizarre material, protein nanowire. But you see that in our analysis, we never used any kind of particular material property in this protein nanowires, other than we say that it helps to create a nanopores in the device. What does that mean? It means that if our analysis is correct, then there should exist a generic agent device that's made from literally any kind of materials, as long as we can punch or find ways to punch small holes, very small holes in these materials. So we tested this kind of hypothesis or prediction, right, by replacing the protein nanowires with literally any kind of material, ranging from biomaterial, organic to inorganic materials. So as long as we find a way we can make small holes in these material, you will see that the device can always produce continuous electricity in the ambient air. Now you see this kind of fluctuation that comes from the fluctuation of the relative humidity, which makes the data actually more convincing. I'm just going to give you a more extreme case. If you look at the right side, right, we have a so-called aluminum oxide thin film, which is not conducting, because aluminum oxide is a compositional material in many of the glass, right, we use daily. And what does that mean is that this kind of material does not even conduct a charge, right? But if we manage to punch small holes, all right, very small holes, nanoscale holes in this insulating material. By the way, there's a commercial way to do that, right? So you will see that if we place a pair of electrodes across the thin film and we measure the voltage, you will see that gradually there's a voltage picking up, right, between the two electrodes. That means even for this kind of insulating material, right, if we engineer nanoscale pores in it, it can be used to generate electricity in the air. Now this kind of generic agent effect certainly carries its meaning. One is that from the scientific perspective, it shows that this is a more convincing and robust effect. Because if I tell you the agent can only be made from certain kind of bizarre, one type of material, I think one's going to naturally question that maybe some unknown substance is falsely contributing to this effect. Second is that from the engineering perspective, it gives us more room, a broader choice of materials, so that if we want a technological development that's going to reduce the material or production cost. It may also give us room for the so-called, turning to sustainable material production. I think, nowadays technology actually produces lots of e-waste. This can be a good problem in the future. So this studio, they made us a nice cartoon about the agent device. I think it actually gave us additional inspirational thinking about that, because the nanopores in the device actually help to capture the electricity in the air and then separate it, right, between the top and the bottom interface, and that's how we can get the electricity. And if we look at this kind of picture, that's actually a very similar process that happens in a cloud during a thunderstorm, because the movement of air water, they create a charge separation between the top and bottom interface of a cloud, and when it reaches to a certain kind of threshold, electricity in the form of lightning flash is generated. So I think in that kind of perspective, we thought that we can consider the agent as a man-made cloud, if you like, because it basically it's capturing the charge from the air water, it separates it, and then create this kind of small lightning, right? That's the electricity. The only difference is that we now be able to controllably capture it. So this kind of controlled electricity, harvesting, putting into a bigger context, as we mentioned before. For example, the air water is really huge resources of clean electricity, and which is evident from the lightning we mentioned before. Lightning still consists of a small fraction of the total electrical energy in the entire atmospheric air water. Secondly is that air water essentially is everywhere. So there's an interesting report that says that even the Sahara Desert has an annual average relative humidity about 25%. And we actually tested our aerogel. It can work in relative humidity as low as 20%, which means that in principle, the aerogel can be deployed anywhere on Earth. Third is that we know that the air water essentially is 24/7 continuous, which means that the device can work nonstop. So this is going to be better than certain kind of energy technology, which is such as solar panel, wind. They're intrinsically intermittent, all right, which means that they're heavily dependent on time and the location. So all those, I would say, grand prospects or hope actually pointed to one central question: can we make it bigger? Right? Can we scale up the aerogel for real useful electricity production? We can tackle on this kind of question by testing some basic principle behind. For example, if we connect multiple of those aerogels together, can we linearly increase the power? And the answer is yes. Now, this is a very simple test. We just connect multiple of those aerogels, with cables in the lab environment. You will see that the voltage linearly increases. So in this case, they can output 10 volt, so which is a typical value. We use lots of portable electronics. So this kind of simple test shows that in principle, we can scale up the aerogel technology by making it bigger, or increase the number of devices. But you may also appreciate that using the cable is not really the smart way out. So I think we can learn from the solar panel. The solar panel uses a transparent electrode so that it goes around the device size. It can broadly collect the electricity being generated without blocking the sunlight, which is the energy source, right? So imagine we can also engineer a type of transparent electrode for the aerogel device. Now, in this case, being transparent, that means it's permeable or breathable to air water. Then you can imagine that the electrode also can go with the size of aerogel device and to scale up the charge correction without blocking the air water that is the energy source. We actually can go a little bit further beyond, because we know that the solar panel essentially is planar technology, which means that you cannot stack multiple panels in the vertical space to increase the power, because light is incident. You cannot go below or beneath the first layer. But the air water actually is diffusive. So, which means it can go along the lateral direction. So imagine that we stuck multiple layers of aerogel device in the vertical direction, but leaving a sufficient air gap between the neighboring layers. So in principle, the air water can reach to every layer of aerogel device. And so then we can increase the power volume without taking up additional planar footprint. So this is like in a big city, right? We accommodate more population by building into the vertical space. So now we had some very preliminary testing showing that if we leave an air gap with a size, kind of similar to the aerogel device, so that's a 1-on-1 ratio, device and the space, the aerogel can maintain its electrical output. So using this kind of symbol data, and we can do a very quick, rough estimate. Now, single piece of aerogel with the size of a fingernail, it can give you around the microwatt power. So that's little power. It barely can light up a tiny little LED dot. But keep in mind that the thickness is only about 1/5 the thickness of a human hair. So imagine we can engineer or make a device big like a cubic meter box, right? Having this 1-on-1 ratio air gap there. So the estimate shows that the power output can rival or even exceed that in the solar panel occupying the same planar space. Of course, you can build further into the vertical space to increase the power volume. Of course, this is a really kind of optimistic estimate, provided that we have sufficient air water flow in the environment. And the added benefit is that you see that since the air water essentially is everywhere, so the AirGen has very low requirement in terms of the location, right? The location choices. I would like to go.
I have a quick question.
Yes.
What humidity are you assuming for the calculations that you show here?
This is about 50%, so that's roughly the average relative humidity, across the year.
Okay, thank you.
If you go to 100%, that number is gonna increase. So,
Another
yes,
question.
yes.
However, I know it's a theoretical calculation, but the practical issue is connecting all those cells, and then the cells will have internal resistance too, won't they?
Sure.
So, yeah, so as the current flows through all of those, you're going to have some voltage drop across all those cells.
Yes.
Yeah, and you have to account for that, I would imagine.
Correct. Now I think that depends on how we're going to extract the energy, right? So if you use a capacitor, that probably is okay because the internal resistance of the capacitor is much larger than your device. So then they can, still extract the majority of the energy from the device. But in the end, we also can reduce the internal resistance. Imagine that it's a thin sheet, right? The larger the size, in fact, the lower the internal resistance, the parallel connection. So you have multiple layers. So.
Yeah, but you're doing an array structure, though, with small. So the surface area is back to small again for the each cell.
Yeah.
So you can't just add the power.
Yeah, then trust this schematic. My thought is that we're going to make as big as possible in the planar way. And you see that the top electrode can be more conductive actually than this ITO, which is a transparent electrode. ITO actually is not that conductive, but in this case, you can use much more conductive materials. Right. So in principle, in fact, this is going to be more advantageous than the solar panel. Solar panel is really, restricted by the ITO material, which is not as conductive as metal.
Excuse me. What here?
Yes.
Over here, to your right, back.
Okay. Yeah, I see that.
What does this do to the surrounding air? Like if I had this in my house, would it dehumidify it? Are you going to dry out the whole planet and we're going to die of thirst? I mean,
I think I mentioned before that the air water is still air water. So if it consumes air water, I think we have good concern on it because you're going to question what else is produced, right? So that can be toxic. But I think the beauty is that the air water is still air water. So it's only the charge part that's extracted. So if you want to dehumidify your house, sorry, this cannot help. But if you're concerned about safety issue, that's good because nothing else is produced. Right. So anyway, we're going to go along this line a little bit further to talk about visionary hope, for example. The hope is that we're not going to use this technology to compete with any of its existing energy technology, but the hope is to complement them or fill in what's not possible. Some energy technology, for example, solar panel, they actually can exclusively take up the space, right? Some strategy to kind of increase space use. For example, as you see in the left image, probably is not the best way out, right? So imagine that we can install AirGen device underneath the solar panel so that it not only can increase the power output, but it can also continuously produce power during the night, right? So in other cases, for example, in the forest, right, essentially it's inaccessible to any existing energy technology. You don't want to cut a tree for exchange. But the AirGen can nicely fit in without harming the environment. In fact, it actually can work better because in a forest or rainforest, the humidity level actually is higher. So you can get even more electricity. So what I wanted to convey is that airgen technology is not going to compete with any kind of space usage. In fact, it's going to just recycle any kind of waste space we don't want for clean electricity. So I can go along this line a little bit further. When the research news came about, the first group of people approaching us was actually a group of artists. They asked if they can incorporate the airgen into their artwork. Now, this is the type of thing that as an engineer, I never would like to think about. But thinking twice, in fact, I think it carries some hidden value behind it. Because existing energy technology, they're clean, but I think they still damage the environment to a certain level. Because at least they stand out in an uninviting way. And it's there, that they go against the natural background. So the airgen, in principle, can be engineered, yes.
Have you looked at the effect of particulates in the air, even like pollen accumulating on the surface?
Yeah, I think that's a practical issue you need to address. But I think, again, solar panel probably faces a similar problem, right? How are you going to...
Was more, more impactful in this technology?
Yeah. I think there's a certain kind of technology. One is that you can engineer surface coating. It's still breathable to air water. Second is that I think there's research ongoing showing that you can engineer so-called self-repelling surface. So it repels the pollutants or particles. At this stage, that's not my concern, but I believe there should be readily technology to protect the surface. Yeah. All right. So what I say is that the airgen device, in principle, can be engineered into arbitrary shape, right? And it can be sneaked into any location because, as I said, air water essentially is everywhere. So in that sense, the airgen probably can be naturally blended into the environment, quietly producing electricity even without you notice. So I call this as aesthetic value because from that perspective, the airgen probably can be, I call it greener energy technology. So anyway, these are grand, visionary hope, and the reality is that we are just a small research group scratching our head for funding and support. But I think many times this kind of grand hope helps, for us to continue on the dirty work, and sometimes in the midst of frustration to continue on this. And we are grateful that we have a good team, and we have some initial support from federal funding agency for this initial discovery. And I think throughout this conference, I hear, lots of AI thing. I record that Dr. Wei Li talk about the concept of AI everywhere. That's essentially computing everywhere, right? So I think underneath this, we need electricity everywhere. So I hope the airgen one day, right, can provide the concept of I call the ubiquitous powering. So to support this concept for ubiquitous computing. With this, I would like to thank you. And if I still have a couple minutes to address your question. Thank you.
This is in the category of one of these things. I hope you're onto something because it would be transformative. We only have a couple of seconds left, and given some of the other time we lost, I really can't go forward with any more questions. But Jun, thank you very much. We wish you all the best, and please come back to us in a couple of years and tell us how you're doing.
Thank you. Thank you, everyone.